Last week, we were introduced to the concept of testing in software engineering. We also delved a bit deeper into black box testing, where we were not really concerned about the insights or the details of the implementation when we are trying to create the test cases. So now we are going to look at just that. We're going to focus on the insights now, and due to the way how white box testing is done, it is sometimes referred to as structural testing, or i.e., the focus on testing the structure of our code, or logic driven testing, which is basically focusing on the logic of the code. So, what is the goal of this so-called white box testing? Well, it is to uncover as many of these nasty things as possible. So, we are trying to figure out, how to implement things in a way that reduces as much faults or problems as possible. So, one may ask, is this closer to verification in testing terms or validation? So the answer, as I've already mentioned, because of how we are trying to figure out a right way to implement things, and not really to figure out, how to implement the right features. So therefore, this kind of a goal falls more under the notion of verification. Okay, so maybe you need to rewind this once again to understand that last statement which I made if you didn't catch that. All right, but moving on. So, how do we actually perform white box testing? So, moving on, how do we actually perform this white box testing? Well, the general idea is to process every single character in code and test for errors. You can also phrase it as processing every single line of code, since this LOC is something that we may be more familiar with from previous lectures. But in general, it is trying to go through every single manifestation of your code, and perhaps this sentence of processing every single whatever and testing for errors sounds a bit too vague. But the idea is really to run through all possible like execution behaviors of your code in order to find faults and then eradicate them. And since this statement sounds a bit too bloated and idealistic, and it really is in practice, it is sort of intractable. All right, it is impossible to cover everything in code. So definitely we would need to have some technique or some guidance of what people have done before in order to help us cover as much of the code as possible. So there are various ways to do this. One of which is the data flow analysis concept, which is based on analyzing definitions and usages of all your variables, basically the things that contain data in your code. So that's one way. But the method that we are going to focus on in this introductory module to software engineering is called coverage. So this is based on analyzing how much of code coverage your test cases have. And the reason why we are focusing on this topic is because this notion of coverage is what most people would be referring to when they talk about white box testing. Let us start with this simplest form of coverage, which is known as the statement coverage, which, as the name implies, the goal is to cover as many statements as possible in your code. All right. So to know how many statements you have covered from your test code, we will use this simple statistic called coverage, in which for statement coverage, we'll have this extremely simple formula of the number of statements executed from your test code that is being ran over the total number of statements in the entire piece of code itself, the entire piece of code here. Okay, to help us understand what statement coverage is, and also as a running example for all the coverage examples later, we will look at this piece of code which we have written like ages ago. And as shown, this is some method called hit from a health component class in a game. Okay, so to give an idea what this was originally coded for, well, if you have played any game at all, you would know that in a lot of games with any form of player character, you normally have this health bar, okay, or health points represented by this health bar that is, representing the virtual health of the player. Okay, so this hit method actually is the method that will reduce the amount of health here, and all this code over here just manages that reduction. And all this code over here basically manages that reduction. If we briefly run through the code, basically this hit function, given some damage value, a certain hit point value which represents the amount of hit points the player has remaining, as well as a certain boolean that indicates whether to show the amount of damage in a certain text view. Okay, so given these three inputs, we will run through the code in this fashion, in which this first block is trying to validate these three inputs. Okay, if it is invalid, we will write it to some logging console and return. Otherwise, we would update the health points in which this new HP equals to your current HP minus the amount of damage. So it's like we want to minus a certain amount of damage of the current HP. All right. So if it is less than 0, we will set it to 0 so that we would not have any negative numbers. Then next, after we've updated the value in the variable, we also need to update the view. All right, so this part actually updates the view. Okay, so what does it mean to update the view? Basically, if this new HP value is less than the max divided by 2, then we would show that the health bar is colored red color. Okay, if the max HP divided by 2, all right, if the new HP is greater than halfway point, then we will set the color to green. All right, basically the health bar to green. Okay, so okay, let's restart. So this next section will update the view as well. So other than restart, so after we have updated the variable to indicate the new HP, we also need to reflect it in the view, which will be handled by this chunk of code over here. So if the new HP is less than the halfway point, all right, then we will color this HP or the remaining HP in the health bar as red. Otherwise, if it was greater than the halfway point, then we will color the health bar as green. Okay, so that is basically what this section of code does. Okay, we also, of course, scale the health bar according to the new value. So we would change this line to a certain new value after we minus off the DMG, the damage value. And for this last chunk of code over here, it depends on this Boolean variable show damage. So if show damage is true, then we would set a certain text view in the app to reflect that using a piece of text. All right, so in the app, somewhere in the app, maybe in this corner, we have that text view which will show the text to indicate how much damage is done. Okay, if the show damage variable is true. All right, so this is what the last chunk of code does. Okay, so let me move this out of the way first. Okay. So as a start, say we want to cover some of the starting statements, say around here, we want to cover some of the statements over here. So we need to determine what inputs will we give to this test that we will create, that will run through these statements for sure. Okay, so let's start to write the test code. Let's just call this test code test1, or call this test code method test1. Okay, the language doesn't really matter here. This is just C or Java-like syntax, but that doesn't really affect what we are discussing here. Okay, so if we wanted to run through this section of code, then we would certainly need to satisfy this condition. So let's just do that by calling the method or the function under test now with the variables that will allow us to satisfy that condition. Okay, so for example, we put -1 as the DMG value, 0 as the HP value, as well as true for the show damage value. And then the next line, we certainly would need to just check whether this is satisfied by using maybe an assert function. Okay, most test frameworks would have this in place. Okay, so we would assert maybe we get the log text, okay, logging text, since we know that we will log this text over here, right? So we would just check for that. So if we get the logging text and we check that it is equals to what we expect, which is invalid DMG or HP values, and if this assertion passes, then we would know that this test case has already passed. So we can see that this test code allows us to definitely go through this part of the code. And we see that there's a return statement here. So we know that if we go through this part of the code, actually all the remaining parts of this method wouldn't be tested. Okay, so we need to create some other test cases to go through those parts of the code. Okay, so now let's move on to the other section that we are interested in, which is this next set of statements that we hope to cover. So let's create another test case that would allow us to cover those statements. Let us now call this test case in a running sequence, test2. Of course, the test case, in a real piece of code or a real test suite, all the test cases should have more meaningful titles. But just for example's sake, we will name them test1, test2 here. Okay, for test2, since we want to cover those that section, we will call the method under test using these variables that will allow us to definitely run through them. For example, we put DMG is 11, the HP is 10, and the Boolean values show damage as true. Okay, so this would allow us to go through that segment. Okay, because it will skip through this since we have DMGs greater than 0. okay, and the HP is greater than 0, and we assume that this max HP is some arbitrary large number, that this HP value is actually not over the max value. All right. Then after we have called the method under test, now we need to make our assertion statements, since this is a test case, and we need to determine whether this is a pass or a fail, right? So the first thing that we do to determine that is to get the output, one of the outputs that we definitely know to be of a certain value. For example, get HP. We imagine that we have this function called get HP that allows us to get the HP value, okay, and we check that it is equals to 0. Okay, this is because since the damage is 11 and the HP is only 10, the remaining HP we have is only 10 here. So if we go and minus 11, we are going to minus off the entire thing. Okay, and when it's less than 0, we would set it to 0. So therefore, we are expecting that this variable, HP variable, would be equals to 0. So this is why we are asserting this. And the next thing that we can assert as well, okay, since we know that it is going to run through this statement, okay, this set of statements, is that we can assert that the health bar is red color, right? So let's just do that right now. We would add another statement here, okay, to, let's say, we have this function that allows us to get the color of the health bar, health bar dot get color, and we check that it is equals to some enum value, red, okay. And so this would allow us to see whether another way of checking that it is what we are expecting to see as a passing test case. All right, so this allows us to definitely go through this. Note that we went through some statements here as well, okay, in particular this and then all the way down here, right? So we know that we covered this, but here we covered some but not all. So let's now create another test case to cover definitely cover this parts, okay. So let's now color this as red color. Okay, so the parts that we want to cover, basically all the remaining ones over here, okay. So we actually already covered the first if brace, and the remaining statements are actually from the else part onwards. Okay, so if I draw this again, the blue color segment covered by test 2 actually also includes the first if in the last part of the code, right? Okay, so really what we want to cover is the remaining after that else part, okay. We'll name this as test 3. Again, in a real test suite, let's name all this in a more meaningful manner. But for here, it's just for example's sake. Okay, so for test 3, similarly, we would use inputs that allow us to definitely go through that set of test cases. I mean, that set of statements. Okay, for example, we have DMG is 1, and the HP, let's set it to the max HP. Remember that it's not very important. We know what max HP is here, but it's some constant, let's say some arbitrary large constant. Okay, but let's set it to the max, whatever it is. Okay, and the last Boolean variable, we set it to true. And now we need to do some assertions as usual to see, to check that the output is what we expected for this test case to pass. Okay, note that if we look at the code, DMG is 1 and HP is max HP. So definitely, we are just minusing. We know that the HP now is full, and then we are just minusing 1 out of that thing. Okay, we would not go into this conditional, and we would go into the else case and continue all the rest of the code. And since show damage is true, it will also run this. So that allows us to cover all the rest of the code that we didn't cover previously. All right. Yeah, so we will add this. So the first thing that we want to check is perhaps similarly health bars color. Okay, so health bar dot get color. Now we know that it should be green since it is more than the halfway point. Okay, then we also check that the width of the health bar. Okay, health bar dot get width, since we know that it will be reset after you minus away the damage to max HP minus damage, which is 1. Okay, of course, again, good programming practices, these values we should probably put it into a DMG variable, but okay, now we're just, for example's sake, we'll keep it simple. Okay, so divided by the max HP. So this allows us to just scale. I mean, this will we are checking that the width of the health bar would be scaled according to the new remaining HP. Okay, and finally we would assert that text view, which we place some text into, since show damage is true, also has the text that we are expecting. Okay, which is basically took 1 damage, and we can pretty much see that this covers all the statements over here. Okay, so that allows us to cover every single statement that we see in this function. Okay, some trivial things that to point out is that, of course, the the method signature is definitely covered, since every time you call the method, definitely you would go through that part of the code. Okay, so that's assumed to be always ran. And other things are like this assertion of this one can pretty much also reside here as a next assertion statement. It can also reside here as a next assertion statement, because you have true, we have placed true here, so we could pretty much also tested that in those two test cases, but we're just trying to keep things simple over here. Yeah. Similarly, this get width assertion, you pretty much should or could also have tested it here if that's something that you need to determine whether this test case has passed. All right, but here we're talking about coverage and not so much of how the quality of our test cases. Okay, so therefore this would allow us to cover every single statement over here. So the question now is, actually, did we cover everything? Well, in terms of coverage, we certainly did, right? If we just quickly run through the test cases again, just to check what is the coverage value. For example, if we look back at test 1, if we only did test 1, okay, so if we only did this, then the coverage number, okay, or the coverage statistic would be equals to number of statements executed, which if we count over here is we ignore the blank spaces and the comments, let's say. Okay, so we covered 1, 2, 3, 4 statements. Okay, anything else we covered? Nothing, because it actually returns here, so that's all we covered. Again, we are ignoring this statement, we are ignoring spaces, we are ignoring comments. Okay, but it's up to you. As long as you know exactly how your statistics are generated, I think you should be fine. So this is 4 statements out of how many? So we have 1, 2, 3, 4. Sorry, we have, yeah, let me just align the text. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 statements. All right, so this coverage value would hence be 4 statements that we covered out of 17 statements in total. Okay, this 17 statements, of course, is with our assumptions that we just mentioned, right? Again, no consideration of this, this, and this. Okay, and in totality, if we did everything, then we actually covered everything, which would allow us to get the value of 1. Okay, so this means we are all good, right? Since we achieved the coverage 1, covered every single statement over here. Does this mean that we have covered all possible manifestations of behaviors of our method under test here? Well, I guess the answer is no, because if you look at this last statement over here, yeah, we covered all statements, but actually there is a hidden, else here, right? Okay, so what if, for example, the show damage is part of a user setting, and if they set it to false, the user doesn't expect to see this thing on the screen. All right, and then you didn't test for this, and somehow there is an error that it is false, and then you will still showing some text. So this is will produce a failed test case. All right, so with this, we can see that actually statement coverage is not enough. That's where we will move to our next technique over here, which is called branch coverage. For branch coverage, our goal now is to cover as many branches as possible, with the coverage statistic now becoming the number of branches executed by your test code divided by the total number of branches altogether in the method under test. And similarly, we will try to strive for the value of 1 for this coverage. To analyze branches, as I've written here, now we need to introduce this concept of control flow graphs, which is basically a way to visualize your chunk of code into a graphical format, as well as really, to convert this code representation into a very specific mathematical representation of your code. And when we do this, when we convert this into nodes and links to conceptualize the flow of your code, then we can make use of various graph theoretical methods to analyze the code. All right, so this is very powerful. For example, you want to find strongly connected components to determine where the loops are, and to find out all the components in loops so that you can optimize them, for example. All right, so let's look at how to do that first before we go to branch coverage. Okay, so this first step is to generate the CFG, the control flow graph. And you can see actually it is quite simple. Okay, it is converting every line of code into a node, okay, and basically linking the different nodes together depending on the executional sequence. So for example, you can see, so now we will treat both the entry method signature as well as comments as part of the code itself. So we will also convert them as nodes, but later on you can remove them if you like to, but just showing as another example that whether you consider them or not consider them, in the first place. In the end, as long as you get your assumptions right, you will still arrive at the same point of code analysis. Okay, so this is the same chunk of code just now. You can see that 5, okay, corresponds to this, the first method signature, which is the entry point of the method. All right, and after we execute this line, we would execute this line, which is 6, okay, which is a comment. Okay, so we compile it, we don't really execute it. All right, we compile it, and we know that it is comment, so it shouldn't be part of the execution, but we just include it here. Okay, just for example's sake, in case any very old or funky language actually treats this as a path of execution, treats the comments as path of execution, then we also include them. But most of the time we will exclude them. For example's sake, yeah, we'll include, and then later on we'll reduce the graph. All right, and the next line of execution is 7. We can see that this is that line. And 7 is slightly interesting because it produces a branch. Okay, it branches out. You can see that the true, or the one of the paths, if this condition is true, is on the left side, which would run through the code 8 and 9. Okay, 8 and 9, and then it will return. Okay, so return means it exits that brace, which is 10. Okay, and goes all the way to exit the function as well. All right, so that's why 10 is linked all the way to 30, which is here. All right, so that's the true part of this condition over here. What about the false part? So the false part is that this condition is false. Okay, you would immediately go to the next line, in which it is an empty line. Again, we'll include empty lines for sake of just completeness as well. And later on we'll reduce them, of course. Yeah, but it would actually go on to this as the next line. Okay, and then 12 is a comment, as we can see here, and then 13 is the next line, and then 14 we can see here, and 14 is yet again this if statement. Okay, so if it is true, it will go through to 15, which is the inside of this if statement. If it is not true, it will just go on to 16, and which is here. Okay, and you can see that there are two incoming links. All right, which pretty much just means that 15 you would go to 16, but if it is false, this would directly go to 16 as well. Okay, and so on. So you can see 17, 18, 19. Yet again, there's another a branch. Sorry, 19 is here. This branch would get executed, and then the true part is here. Okay, the false part is here, and you can pretty much run through the rest of the code, and you can see that it ends at 30. Alright, if you're having problems, of course, you should pause the video and then try and figure out exactly which of the nodes correspond to which of the lines over here. Okay, make sure that you convince yourself that this is a corresponding CFG of the code. Okay, as promised, the second part of this is to condense the CFG. The condensed version of the graph is this. So we can see that 5 is the entry point, and we retain the entry point, the method signature. You can also remove them if you are consistent across all of your code analysis. Okay, so after 5 we have 6, then we have 7, which is the if statement. Okay, and then from 8 to 10. Okay, because definitely 8 would go to 9 and go to 10. there's no reason why we want to reflect that over here. It's just wasting of the space to draw this, as well as computational space if you are throwing this into some algorithm to analyze, right? So we can pretty much make that into one node. Okay, so this chunk of statements 8, 9, 10 definitely executed together. I mean, definitely executed in sequence. So therefore, we will combine them. Similarly, if we look at this part over here, 11 to 13 are combined, because from 11 to 13 they will definitely be executed in sequence, so we bunch them up as one chunk of code. All right. Um, let's just do one more example, like 22 to 24, right? 22 to 24 is here, 22 to 24. So this one will also always be executed as one chunk of code in order that we see here, 22, then 23, then 24. So therefore we can bunch them up as one single node, okay, instead of splitting them up and wasting both your drawing space as well as your computational cycles if you are analyzing this in some code. All right, so this is the condensed version of the CFG. And once we have the condensed version of the CFG, we can now, try and come back and look at our goal of branch coverage. All right, covering as many branches as possible. And we can see very clearly now with the CFG that the branches are all this. Okay, the branches are all, all these sections that we are interested in. Not this, okay, this. Okay, means that as long as we have a branch, we want to cover both sides. As long as we have a branch, we cover both sides. Branch, cover both sides. Branch, cover both sides. So that is our goal. So let us just do that. So if we continue from the previous example, right? The previous statement coverage example over here, we see that test 1, test 2, test 3 already covers some of our branches. So let's have a look over here. Like test 1, okay, is this. Okay, so test 1, actually if we draw it in the same color, test 1 has already covered this side of things. Test 1, okay, and test 2, if we look at test 2, okay, test 2 is this chunk of code. All right, or rather test 2 would be this chunk of code, right? And for the branch that is included in test 2 is actually the true part of the branch in the second conditional. So therefore test 2 actually covers the branch over here. Oh, let me just, okay, test 2 is covering this branch. And we can also see that test 2 covers the true branch of the branch that is started at the node 14. Okay, if we look at node 14, okay, node 14 is this, 14 is this, and for test 2 it actually is having true for that branch, right? So therefore test 2 also covers this. Okay, let's keep it as the same blue color. And continuing, for the branch at 19, the branch at node 19, this branch over here, this branch over here, it is also covering the true part, okay, for test 2. Okay, all right, and that is all that it covers. Okay, and you can also treat it as it covers the 28 as well, but you can also leave it for the last test case, okay, which is what we will do over here. So the last test case in red color, if we take a peek at what it is again, it is trying to cover all the rest of the test cases here. So if we continue, what we are covering over here, you can see that test 3, let's have a look at it in detail. 19, okay, so for 19 it covers the else case. This is the node 19, okay. You can see the test 3 actually goes through to the else part. Okay, so this is test, oh sorry, test 3. All right, and test 3 also covers the true part of the last one. I mean, this one can pretty much be test 1 or test 2. Those two test code also goes through this branch, but we'll just label it as the red color over here. Okay, or you want to just use all the 3 colors also can. But the main thing is we know that this has been covered, and we are trying to cover the remaining ones. Okay, sorry, I left out one. Okay, because test 3, right? If we look at note 14, note 14 is here. For test 3, it also covers the false side of the branch if you look at the code again. Okay, so this is also test 3, the red color. Okay, so with all the tests in the previous case, for the statement coverage, if we just run through all the tests from the statement coverage, we can see that it has covered most of the branches here, except for one last one, which now it becomes clear because we have the CFG, which is this one. Okay, so this one is not covered by all our statement coverage test cases. Okay, so this is what we need to add here if we wanted to do a branch coverage and try to reach for the number 1, right, for the coverage statistic. Okay, so we need to add, I'll just use a plus here, plus test 4. Let's label it as test 4. Okay, and the value that we need to input in order for us to reach this last branch, we need to look at the code obviously, is to reach the else part, the hidden else part of this. Okay, so we pretty much just need to focus on that last value. Okay, and make sure that the damage is less than your HP so that it actually goes all the way to the end of the code. Okay, and once we put a false value, we would definitely go through to that hidden else case. Okay. All right. So this would allow us to have once again the coverage value. Oops, sorry. The coverage value, which is now a branch coverage. Okay, branch coverage value equals to 1. In other words, we covered 1, 2, 3, 4, 5, 6, 7, 8 branches out of all 8 branches that we have. So if, for example, we only covered, like in the case of only using the statement coverage test, that means test 1, test 2, and test 3. If we only had these 3 tests, if we want to find out how many branches we covered. So if we only had 3 tests, okay, if only these 3 tests, then the branch coverage value would only be the amount of branches that were covered by these 3 tests, which is 1, 2, 3, 4, 5, 6, 7. And we don't have this one, because this one is what we added just now, right, on top of the 3 tests. So that means this would give us a branch coverage of 7 out of 8, okay, which is less than ideal if we had compared to when we had the extra last test over there. All right, so this is branch coverage. That whenever you have a return statement, exit, the function, right, it has to go through, this single exit point. Okay, otherwise your calculations would be messed up if you missed out on this. It's what I realized in past student work, that sometimes you put exit as somewhere else, but actually the function only has one exit point. All right, so all the return statements, please exit at the right place. Okay, the other thing is by convention, normally we have one node as a single node as the entry point. But that is not the most important thing. It's just cleaner. Okay. Okay, so that is branch coverage. So the question now is, again, have we covered all possible permutations or manifestations of behaviors through our code? All right. So the answer is obviously no again. Okay. And to really cover everything, let's go on to the next concept, which is path coverage. Okay, so for path coverage, now instead of looking at only the branches, we now want to cover as many paths as possible. So the coverage statistic that we have now is the number of paths that is executed through your test code or test suite in totality, divided by all the possible paths through your code. So let us see what this means with our example code once again. Similarly, we would first need to generate the CFG. And here we have the same reduced CFG that we had before, a clean version of it. And firstly, I think we need to define what do we mean by a path. So in graph theory, a path basically means a set of nodes or links from a given start and an end point. And in this case, the start and end point that we are interested in is basically the entry point of the function as well as the exit point of the function. And our goal here is to really cover every possible path through the start and the end point. All right. So in our simple example over here, I think we can probably enumerate through all the paths, but in more complex examples, it may be a bit of a more daunting task. Let us just do this for our simple example over here. And similarly, we continue from where we left off from the branch coverage example. Let us look at what are all the tests that we have from branch coverage, basically the 3 tests from statement coverage as well as the additional test from branch coverage, and let's see what are all these paths that we have covered if we are going through this test suite of 4 test cases. Okay, so for test 1, which we had used green color, test 1 basically goes through this path. So if you need to rewind and look at what test 1 is, please go ahead and do so. But you can basically see that test 1 goes through this path. Okay, and test 2 was blue color. Maybe we'll quickly look at what test 2 is. Okay, so let's just recap. Test 1, we just drew this. Test 2 is this path. Okay, so let us draw it in the same blue color onto our new cleaned up CFG over here. So test 2 similarly starts from here, and the path it goes through is here to the right and all the way on the left side here, and then left here and all the way to the end. All right, so this is test 2. Let's label this here. Now let's look at test 3, or before that, let me just fill in test 2. I didn't write the word 2, the number 2 over here. Okay, so test 3, we take a peek back at what test 3 so this is test 4. Alright, so after drawing all the paths, you can see that if we were just aiming to cover all the branches, obviously we have gone through all the branches as we know before, okay? But what did we not cover? Remember that white box testing, we are trying to achieve our goal of all the different permutations of possible behaviors given whatever we define as the possibility, which in this case are the space of possibilities, all the paths. All right, so this is actually not all the paths. You can see that for example, this path which goes to the right and then the left and left again. Okay, and we'll call this test 5. And you can see that test 5 covers a path that has not been traversed by previous paths before, i.e. this is a unique path that contains a set of nodes or links that is different from any other ones before. Okay, so this is a pretty small piece of code, so we can probably enumerate all the paths, which we are not going to do here in the interest of time. But if we look at a more complex function that runs maybe 100 times, and inside the loop there is if statement, whatever is in here, and then there's a set of statements here. So even this simple loop that is within the function would actually blow up the number of possibilities in the loop, right? This actually means that we would need to run like 2 to the power of 100 times if we really wanted 2 to the power of 100 test cases, if we really wanted to cover every single possible path through there, right? Because it may be the case that in the first loop, the first iteration we choose the left side, the second iteration we choose the right side, third iteration we choose the right side again, and then for the second time we for the second test case we would choose the left side, and then right side. For the third iteration we choose left side, and so on. So if we go through this for 100 iterations of the loop, it is almost intractable to run all the test cases like this, especially in the totality of the entire software. It becomes really impossible to do that. Okay, so we do need like some theoretically backed foundation that allows us to be confident that the number of paths that we choose to go through actually gives us confidence that we have covered enough ground. This is where we can move on to this testing approach for white box testing called the basis path testing approach, which is based on this number called the cyclomatic complexity. Before we go there, just a note that there are more types of different coverage approaches. Okay, we have covered this statement, branch, path. There's also a coverage that focuses just on the conditions. There is also branch and condition coverage. But in the interest of time, we will not go into details of what these things are. But certainly, a quick Google would allow you to find details about how this other different types of coverage works. And given the foundation that we have over here, I believe it will be very easy to extend your knowledge to these other different types of coverage techniques. All right, so from the 3 types that we have, sometimes you want to ask like which coverage to use. That is always a question that depends. Okay, it depends on many different aspects of what your project the constraints are, right? If you need to do it in very quick time, you don't have a lot of tools to work with, the statement coverage is probably the easiest to apply. But if you really need a very robust test or very comprehensive test that covers all possibilities in a critical system, that you just want to reduce the failure rate to very, very low, because it is so critical to eliminate all bugs, that probably you should go towards a more path-based approach. All right, so this is more comprehensive. Okay, but as mentioned, it is often intractable to do everything. Okay, which is why now we are going to talk about this notion called cyclomatic complexity, which is here. Okay, so what is this cyclomatic complexity, you may ask? So as shown over here, it is a formula, and this formula includes this three variables. Okay, and these three things are nothing more than what we already know. Okay, like let me just annotate them. This is referring to the total number of ages. This is referring to the total number of nodes in your CFG after you have generated a CFG, obviously. Okay, and this P, sorry, let me just pick the correct pen. This P is referring to connected components. Okay, if you remember your graph theory, connected components just mean a set of nodes that are connected together. All right, and more often than not, this value would normally be equals to 1 if we were just working on one method, like what we have over here. We just have one connected component. If you actually had multiple different methods, then you may have two connected components. Like for example, if your analysis was done on a class with two methods, okay, so and you wanted to calculate the cyclomatic complexity for the entire class, then you would have two there. Okay, but here we just keep things simple. We are just looking at one single method. All right, let me just erase this. Okay, so we'll just jump right in and try and calculate this value, okay, called the cyclomatic complexity, abbreviated symbolically in mathematical notation as V bracket G, the V value of the graph G. Okay, assuming that our CFG is annotated by the symbol G. Okay, first thing, calculate the number of edges. Okay, so number of edges, we will just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 18. Okay, so this means that E is equals to 18, and let's calculate N. Maybe we use a different color, and N, we just count the number of nodes, right? 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this N value is 15. This P, as we mentioned, it is 1. So, we just replace it by 1, and we will calculate what the value of this is. Okay, so 18 minus 15 is 3. 3 plus 2 is 5. Okay, and the cyclomatic complexity for our graph, for our CFG, is 5. And what does 5 mean? So this 5 actually is referring to the number of paths that have that you need to write the test cases for, at minimum, to have sufficient, so-called sufficient coverage. Again, we will not go into the details of the theories that back this statement up, but generally you can just treat this as having a high probability of uncovering the bugs that we so hate. All right, bugs. Okay, so once you have this number, next what we want to do is to generate the test cases, right? But before that, we need to know which are the paths that we want to generate test cases for. We know we want up to 5 paths, all right? But these 5 paths, we also need to have a structured approach in order for us to do a coverage that is enough, to go through the minimum so-called baseline set of paths. Okay, so first you pick a baseline path. Okay, this baseline path is basically any path with that goes through the most number of decision points. Okay, so for example, we can have this path starting from here. 7 is the decision point, so we choose the right side because if we had gone through the left side, there's no more decision points and we would just hit the end over here. Okay, so we would choose the right side here. Okay, and then we go here, and okay, 14 is another decision point, so we need to choose the one that goes through more decision points. Actually, it doesn't matter left or right. Okay, we would still come to 19. Okay, so once we're at 19, we would again need to choose left or right. Again, there are no difference in terms of the number of decision points that we would result in. Okay, so we would just go through all the way to the end. Okay, because it doesn't really matter from this point onwards. We would have chosen a path that goes through the most number of decision points. Okay, so after this, you would backtrack the baseline. Okay, so again, let's use a different color, backtrack the baseline. So this is now the baseline path. Okay, so using this baseline path, we would backtrack until the last decision node and then flip the decision to go the other side and continue the path to the end. So what it means is that, okay, baseline path, we would create the first test case for that, and then for the second test case, we would backtrack the first path to the first decision point, the last decision point that we went through. Okay, and then go the other way to create another path for a test case that we will write. All right, so what this means is that we will generate this second test case through the same path all the way, same until here. Okay, we branch the other way. All right, so this we would call test 2, and then we would backtrack from that point onwards once again. Okay, until all the decision points are covered. Okay, so here is where we left off. We will go backtrack, and this is the other decision point. So we would go this way. Okay, and then so this means that now we use another color. Start here, follow all the way the same thing until this decision point. We branch off here, and then do the same thing. Okay, call this test 3. All right, then next test 4, we were here, so go back until decision point, yes, here, then we will branch off to the other side. Okay, so let's do that, and therefore test 4 is like that. Branch off here and follow the last path, and this is test 4. So we are reaching the end. Now we have one final one, and you can see why it is the cyclomatic complexity number is 5 now. Let me choose orange color, haven't been used before. Okay, so we were here at the last point, and so the very last decision point is here. So what we need to do is to go the other side. Okay, So that's what we will do. Start from here and this way. And this is test 5. And we are done because the total number of tests here equals to the number of tests we are aiming for, which is this number 5. Alright, so this is the method that would allow us to create this sufficient coverage number of test cases. Okay. The final step, of course, is to create the test cases. That means write out, the actual test inside here, with calling the actual method under test and then doing the proper assertions in order for us to figure out whether our code is doing the right thing. All right. So that is all the difficult concepts in this class. And this next graphic over here just shows the many different popular test libraries that support this coverage concepts. Okay, things like JUnit, which if you have done Java, certainly you have heard or used it before. Espresso, if you have done Android programming, and then some other cross-platform ones, which you can go and Google if you are interested to find out how to use them yourself. Okay, and this is just a screenshot of a typical coverage report that you can generate. This is from React, so you can generate the test coverage by just running the console commands. So lastly, I just wanted to place what we have covered so far in the context of our testing process that we have mentioned. Okay, so remember that for testing, we also need to follow a process to get us to the test cases that we want. Previously, we have seen decision tables, we have seen state diagrams, which are methods to get us to this stage, which uses different kinds of inputs to our test design. So in the context that we are discussing here for the white box testing using a coverage kind of a method, is that the specifications of our system is represented by the code in our implementation, plus the CFG that we have created as an abstraction of our code. All right, so this will basically be the inputs into our test design. Okay, maybe there's a loop here, and the testable features that we are trying to extract are basically the basis paths. Okay, the paths that we will want to aim to go through. This is a set of stuff, okay, a set of nodes or links to represent the paths that we aim to go through. And the inputs and outputs which we need to define are basically, given each one of the paths. For example, P1, we want to choose the right arguments, okay, ... and determine what is the correct expected output for each one of the paths that we have demarcated, right? And finally, with the inputs and outputs defined for each of the paths, we can finally write the test case. Test 1, for example. Okay, so we'll call the method or function under test using the arguments that we have defined, and then assert the, for example, the output, whether it's equals to the expected output that we have also defined in the last step. Okay, so this would give us a very structured, well-defined way to approach our test design using this white box testing approach based on coverage. And that's the end. I'll see you guys in class.